This is not random. Most shaders use the Sine hash function. It's fast and easy to write, but it doesn't produce white noise, breaks for small and large values, breaks across platforms, and is a pain to tweak. In this video, I'll show you something better, a hash that works across the full range of float inputs, about 90 orders of magnitude, compared to 5 or so of Sine hash, stays consistent across GPUs, and avoids visible artifacts, all without floating point math or texture lookups. So, what is a hash function? A hash function takes an input, like UV coordinates, and returns a pseudo-random number, usually a float in the 0 to 1 range, that's consistent for the same input. Let's look at why float-based hashes fail, and how a uint-based hash fixes those issues with simple, bitwise operations. Let's quickly compare the properties of the Sine and uint hashes. First, an ideal hash produces evenly distributed, pattern-free values in the 0 to 1 range. The Sine hash produces visible stripes, while the uint hash gives white noise. Second, the same input must always give the same output. Floating point math varies across GPUs, so Sine hash outputs can differ, while the uint hash is bit perfect everywhere. Third, good hashes handle all input ranges, from small to large values without artifacts. Sine hash breaks outside a narrow range, while uint hash remains stable. Fourth, both hashes are fast, but the uint hash avoids unpredictable precision issues while matching Sine speed. And finally, Sine hash is limited to a 2D input and a 1D output. Extending it is difficult and adds complexity, and possible artifacts if done incorrectly. Uint hash scales easily to any input or output dimension. With these issues in mind, here's the solution. A uint-based hash. It has 5 steps. First, we convert the float to a uint using float bits to uint, which gives us its exact binary representation. From there, work entirely with unsigned integers, since integer math is both fast and precise on GPUs. Second, correct any inaccuracies caused by float coordinates. Third, mix the float bits using a uint to uint hash to generate a unique seed. Fourth, we finalize that seed to produce a high entropy, uncorrelated output. And finally, we reinterpret the result as a float in the 0 to 1 range by constructing a IEEE 754 float using bitwise operations. Now, let's break down each part of the uint-based hash in more detail. For this example, the hash takes a vector 3 input and produces a vector 3 output. We convert the float inputs into bits using float bits to uint. To understand what's happening, let's briefly review how floating point numbers are stored in memory. A float has 3 parts: Sine, 1 bit, indicates if the number is positive or negative. Exponent, 8 bits, controls the magnitude or scale, and is stored with a bias of 127. Mantissa, 23 bits, contains the fractional digits of the number. Visually, we represent a float as -1 to the power of Sine times the 1 dot mantissa times 2 to the power of exponent minus 127. Notice something important here. The first digit of the mantissa is always assumed to be 1. It is not stored anywhere, but implied. If the exponent is 127, that means the exponent is 0 after biasing, so the float falls between 1 and 2, and the mantissa directly represents the fractional part. When a float is between 0 and 1, the exponent is smaller than 127, meaning both the exponent and the mantissa determine the final value. For example, both 0.5 and 0.25 have a null-zero mantissa, but different exponents, making their magnitude differ. This exponent difference between the 1 to 2 and 0 to 1 ranges matters. We'll use this knowledge later to generate floats efficiently in the 0 to 1 range by building mantissa bits in the 1 to 2 range and subtracting 1 to isolate the fraction. Now that we've converted our float bits to uints, we need to handle the -0 edge case. In the IEEE 754 float, -0 and 0 are equal in arithmetic, but have different bit patterns, so different hash results. This can be an issue in 3D engines, where transformation math or game logic can produce -0. This is not bad on its own, but bad for our precise hash. A plane at the origin might hash differently, or even flicker if it flips between 0 and -0 across frames. To fix this issue, add the smallest non-subnormal float, about 1.18 times 10 to the -38, This tiny value converts -0 into a small positive number, effectively eliminating -0. While any addition, even 0, can change -0 to 0, adding 0 might be optimized away by compilers. Adding a subnormal float can also be optimized away on GPUs that flush subnormals to 0. Using the smallest, normalized float keeps behavior consistent across GPUs, with no visible impact, since any precision loss only matters at scales as small as 10 to the minus 37. Another option is explicitly checking if the input is -0 and replacing it with 0. This preserves other values precisely, but is slower. Ideally, avoid hashing floating point inputs altogether. For instance, when using float coordinates in integer steps, like in Perlin noise or screen coordinates for screen space effects, convert them to uints via float to int to uint. Direct float to uint casts are undefined for negative numbers, and float to int overflow is undefined in GLSL. Casting floats to int maintains exact values up to plus or minus 16.7 million, and the int to uint conversion preserves the sign and value accurately. This remains precise within the range of plus or minus 2.1 billion integers, breaking only when the float itself loses precision. Step 3 is mixing. Now that we've handled edge cases, we combine multiple inputs efficiently by preserving randomness. After converting each input into a 32-bit uint, we pass them sequentially through a uint-to-uint hash function, ensuring they're properly mixed. The uint-to-uint hash function I'm using is on screen. You may be surprised that such good noise is achieved with so few operations. Using a reversible hash is important here, because it guarantees that every unique input maps to a unique output, so no entropy is lost. Without that, each iteration would start collapsing different numbers into the same value, reducing randomness. Entropy is a measure of unpredictability. A 32-bit uint can represent about 4.3 billion values, providing 32 bits of entropy. A 32-bit float also has 32 bits, but slightly less usable entropy, since some bit patterns represent special values, like nan or infinity, which aren't meaningful coordinates. To produce unique hashes for each output component, simply reorder inputs, for example using XYZ for one output, YZX for another, and so on. This breaks up correlations between outputs while preserving the full 96 bits of input entropy. But what if you're hashing a vector 3 into a vector 4? Now, you could hash each output component individually. That's 12 hash calls, 3 inputs times 4 outputs, which is expensive. A faster method is to pack all 3 inputs into a single 32-bit seed. Then, run one additional hash per output component. This is faster but reduces entropy from 96 bits down to 32, so you can optimize for either speed or quality, depending on your use case. Step 4 is finalization. We mix the inputs into a single uint seed, but we lost entropy. To fix this, we re-inject entropy by using a unique input component for each output. Output.x is hashed from inputs xyzx, output.y from xyzy, and output.z from xyzz. This retains all 96 bits of input entropy. If inputs match or exceed outputs, like vector 3 to vector 2, just assign different inputs to each output component. If outputs exceed inputs, like vector 2 to vector 3, entropy is limited, 64 bits here, causing overlap. To avoid this, assign each output a unique magic number. This prevents collisions and improves hash quality, even if enough inputs exist. Also, watch out when using identical inputs in multiple hash functions, like vector 3 to float and vector 3 to vector 3. To avoid accidental collisions, vary the initial value per hash, such as setting it to the number of outputs. But more than 32 bits of entropy doesn't visually improve noise. You already get billions of unique output values, but extra entropy may matter for simulations or extensive RNG use. At this point, we have a random 32-bit unsigned integer, but what we really need is a float in the range 0 to 1. The most straightforward way to do this is dividing the float by the largest uint possible. Float rand uint divided by max uint, value as float. But division is slow and can lose precision. A better approach is to use the structure of the IEEE 754 float. to the conversion directly with bit operations. This gives us a flow with 32 bits of randomness, which is the practical maximum for a single precision flow in the 0 to 1 range. Here's how it works. First, isolate the mantissa by removing the sine and exponent bits, either masking or right shifting by 9 bits, which is faster. Then, order result with the float bits for 1, so 3f8 followed by zeros. Finally, subtract 1, putting us back into the 0 to 1 range. This works well because the float format handles exponent scaling automatically. All you have to do is build the mantissa. You can randomize the exponent to squeeze out nearly 2 extra bits of entropy using a different conversion, but that adds complexity and doesn't improve visual quality. For discrete values like 90-degree rotations, you can use a much simpler method. Just take the random uint, mod 4, cast it to a flow, and multiply by pi by 2. Now let's compare the uint hash to the sine hash in terms of performance. To test this, each pixel is hashed once to display. To confirm the output looks random. Then in a loop, I rehashed each pixel with a slight offset to prevent the compiler from optimizing it away. To make sure the loop still runs, its result was added to the output and multiplied by a small value to avoid changing the color. The benchmarks use the 512 by 512 resolution with 100,000 iterations, average over 10 seconds. VSync was disabled to avoid capping performance. All results except the vec3 to vec3 with entropy use the faster uint hash without entropy reinjection. For vec2 to flow, which is the same format as the sine hash, the uint version is 22% slower. But for vec3 to vec3, the uint hash is 31% faster than sine. And even the version with entropy reinjection is still 9% faster than sine. I also tested on a laptop with an integrated GPU and a phone, and got similar results. Of course, I can't test every system, so exact performance may vary. But overall, the uint hash performs close to sine in 2D, and better in higher dimensions. To use the uint hash in your project, go to the link in the description, copy the code from the README, and adjust it to match your needs. If you need examples or tips on customization, check out the uint hash GD shader inc file. The Godot project also includes scripts for measuring performance, so you can experiment or even build a better hash.